more. And if the teacher is saying, I don't know what this computer thing is doing, it's not working, it's a black box, and they're scared of it, that translates to the girls, especially in the classroom, because most elementary teachers are girls, of not knowing it. And so we feel this is a very important step towards diversity. So we have this whole guide to running a STIG. And so the other link that's on that same slide takes you to this page. Now, remember, we did this over multiple years. And so this is the last year's content. So the introduction is what a STIG is and why it's important. Notice again here, the facilitators of CT practice, the CT inquiry group for reflection, and then small group lesson plans for to have them actually create a lesson plan. We started with seeds and then went to lesson plans. So we had, for each of the topics, we have this structure, a presentation, an activity, and then how are you going to integrate it? Because without that integration piece. The other main thing we did was to create a more simplistic, I'm going to zoom a little bit so you can see it better, simplistic model of what computational thinking is. Because the big ones that have so many pieces were overwhelming. So we wanted to have data as a portion, simulations, how they would be created and used, programming, a necessary part, and systems thinking sort of caught some of those things that weren't in any of the other ones. So we have examples for each of these. And then our content for the STIG, here is based in those areas so that we could make sure we had all of that content copied. But then we have additional resources from the previous. But just to let you know what's here is we have the agenda, and the agenda we left in Word form to post, which is not going to show, but you can click on it and go, because people will do this different ways. As in, some people could, we went from having Saturday type activities. We've tried having evening, so it was after their school day was done, and having more shorter ones, or the Saturday were longer ones. So this agenda can be tweaked to make it work, but then you'll have all the parts. Then each one had a presentation on that content. Then there were parts that are linked from the presentation usually, but or from the agenda, that have things like a vignette. One way we tried to figure out how elementary teachers view computational thinking is we gave them a story of a teacher who teaches a lesson and asked if they saw computational thinking and how they saw computational thinking in that lesson. And we got both types of answers. Lessons that weren't intended to be computational thinking at all, we had people telling us how computational thinking was in that lesson. And then we had other ones where people didn't see the computational thinking. And so then we had discussions about it rather than saying, you know, computational thinking is not that, because how people see it is so different. And then we had an activity that they did, and then how they designed that lesson. And each one is more fully defined here. If you click on it, you can see. But let me just give you an example of, let's do models and simulations. And if that opens, I'm going to open in a new tab so that Oh, that's the doc, sorry. Just a second, I have to go this way to. Okay. Just going to one of the simulation pages. So we found a whole bunch of resources about different simulations. Now, I don't believe using a simulation is computational thinking, but when you talk through how this simulation is used to how it would be created, and if you can change variables in it, that's usually enough to have them understand why simulations are part of computational thinking. So there's lots of them. They're sort of fun things to do. So you can choose whichever one fits into the area of science you happen to be doing at the time. And so teachers have that. Okay, I want to check one thing. How many people do we have? Okay, we have 9 people in the room. So I want you to experience one activity that was made doable because of the, or I can do online. All these STIGs were done in person because this was all done before COVID started. Okay, so I'm gonna go with 4 volunteers because I don't think we have enough people for 5 in each room. But can I have 4 people who raise their hand? And if you don't know how to raise your hand, it's under the reactions and then raise hand. Okay, so we're going to say, Paulette, you are number 1, Charlotte number 2, and Angela number 3. Can I have 1 more volunteer? Okay, Erin, you're number 4. So the 4 volunteers that I got go into this link that says group 1. And everybody else who didn't volunteer, I'm sorry to tell you, but you don't get out of it. You go to group 2. Okay, so when you go to group 1, there's directions on the first page. And when you go to group 2, there's directions on the first page. And because group 2's work is a little harder, they get to unmute and talk to each other. Group 1 just sort of ignore that. And I'll give you 3 minutes to work on this. Okay. And I'm going to go see if there's anybody in group 2 doing what they need to do. And I'm going to stop sharing while we do this so that you feel I'm not watching. Okay.
Would you share again? I couldn't get the link to open.
Oh, I'll put it in again. Hold on a second.
I tested
It's
them
in
all.
the chat. So try now.
So group 1 and group 2 are both in the chat?
Yeah.
Yeah. So group 2, oh, I
I'm in
typoed here.
group 2.
Okay, so group 2, the first thing you have to do is type your names here or next to a number on a sticky note. I will be in group 2 also, so. Oh, okay. Yes, we can paste them in like the old-fashioned way. Okay, so now group 2, we all go to the second slide, and there's a bunch of words here. We get to work together, but we have to turn these words into sentences. Okay, so we move them around. Computational thinking, those will probably go together. And we can talk as much as we want. Notice a capital letter. We'll probably want that at the beginning of a sentence. And group 2 might want to unmute because this is going to be hard to do if we're not talking to each other because you'll move something. And in group 1, I hope you read all your directions.
So we remove it for everyone, right?
In group 1, when you move it, everybody moves. So that's why you might want to talk to each other.
Yeah. I'm in group 2.
2.
Yeah.
Okay, yeah. So talk to your fellow group members because you're working together on this.
So I'm trying to move any of them that have capital letters to the far left of the board. So that's my.
Okay, that's good. And with group 1, read the directions. So I see a check mark when your part is done. When your one slide is done. And if one of you wants to go on and do number 5, that's good because I didn't have quite enough people for what I wanted to do.
So is someone helping me right now in the 2 for group 1? Because I thought we were working separately.
Yeah, you are doing only the green ones.
Okay.
I just came into yours to look, but I didn't move anything. And Erin is doing the pink and Paulette is doing the blue.
Okay, I'm in the green, so that's probably the problem.
Okay. You typed your name on a thing that was a different color, so
Yeah,
stick
I
with your
did.
color. Charlotte caught you.
Well, I thought I was in, it's showing that so I'm blue.
Yes.
Okay.
So go to the, or who are
It
you?
said this,
Sorry.
it told me to go to slide 3, but then this is slide 4.
No,
I
the
think.
slide that has the number in the top left corner.
Yeah,
So it's
yeah.
off by 1 error. But the 1, 2, 3, 4 is in the top left corner. Don't look at the slide number.
Okay.
And I see somebody is done. As Angie, you're done. Could you also be number 5?
Next generations.
Putting words that go together, like next generation.
Yeah, so I'm thinking,
Okay.
yeah. I'm thinking it's next generation science standards.
Good.
Are these connected sentences or just,
Yes,
oh, okay, all right, that helps.
Will we see everyone's at the end?
yes, I'm going to share the screen.
Unless I see two, I don't know if I'm right on three.
You can actually go to the other one.
Okay.
I'm going to help you out a little. Charlotte. Okay. Okay.
I'm baffled.
Thank you.
Okay, actually, the group one is almost done.
Yeah, of course.
There's some science standards. I'm going to modify. Okay, actually, group one is done. So we're going to call time on group two. Because I believe you'll never get it done. So we're not going to wait. Okay, so I'm going to go back to sharing my screen because the principle, just a second, I have too many things on my running right now. Okay, this is the sentences that group two were able to make. If we go to group one, it says, science and mathematics are becoming computational endeavors. This fact is reflected in the recently released Next Generation Science Standards and the decision to include computational thinking as a scientific core practice. With this addition and the increased presence of computation in mathematics and scientific contexts, a new urgency has come to the challenge of defining computational thinking. The principle they were learning here wasn't necessarily that definition, which came from Weintrop's paper on the definition of computational thinking. For elementary schools students, I don't recommend using a research journal article, but I thought, you know, for years, I thought we could take it up that notch. But what we showed here was the benefit of parallel processing, because the five individuals, we're going to pretend they're five individuals were each able to do their part. And since once they all understood where they were supposed to be doing their part, it all worked together to make a sentence, or make a collection of sentences. Where the other group, if in person, this works a little better because the group that was trying to do it non-parallel was much louder than you guys were here. But doing it as a group, you still have the same number of people hours working on it, but it doesn't get done. Then in the upper grades, you can then talk about how it's different, you know, what things had to be different. For example, the words were already sorted for the people in group one, sorry, not for the people in group two. I thought about giving it to you in color, you know, the same colors for group, and that's why one and didn't change color. But there was no other reason for that and to be blue other than that. But notice how getting this concept of a high-level computer concept doesn't need any computing at all, as in we didn't need to have the computers or talk about timing. But in this concept can be differentiated at different levels. You know, make something easy that's and just talk about it taking less time, or for the older kids, talk about how it has to be prepped and there has to be multiple levels. So, you know, that's just one example that we used. We had lots of others to show all different kinds of things, data collection issues. The teachers have a hard time differentiating though what is data collection for science and what is computational thinking applied to data collection. And so we had a lot of discussion around that in order to help them see that yes, it's a big gray area overlap between the two, but there is a part that is separate from the data collection that you do in science. So I want to hear from you on if you go back and look at the lesson plans, what kind of lesson plans do you think you'd be able to do with your elementary pre-service teachers and hopefully their mentors, so we fill that gap and get them prepared? So, any thoughts?
Can I just answer a quick question about
Sure.
what you were saying about data collection versus computational thinking and data collection? Are you talking about data collection versus analysis of data? Is that what you're referring to?
Not necessarily, because analysis of data can spill over into the math.
So are you
standards rather
talking
than
about the
computation.
methods, the methodology to collecting good data? Is that?
The methodology and what other features you have to think about when you're talking about computer data.
Okay.
For example, we used the citizen science data and how you can collect that kind of data, if you know what citizen science is, that you can,
Yes.
okay. It collects lots of data. The only way to do that is through computational methods. You have to be applying computers in some way to collect that data. And so we talked about how that data could be collected. This was in a lesson for probably fourth, fifth grade, that how the computers had to be connected and the data had to be shared. So getting that networking concept in there. And then when we looked at the citizen science data, there's a lot of data, and you wouldn't be able to go through that by hand to find patterns in it. And so how the computer can help you
So
do that.
really, you're talking about justification for using computer technology to be able to use that data.
Yes, but also then the process by which it gets done. So the
Okay.
algorithm and things like that got in there too,
Okay.
that you have to be thinking about
Okay.
the
So it's
steps.
really a global picture about what you mean by computational thinking. Okay.
Well, in that one example, I applied different parts of our model,
Okay.
you know, not just the collection of data, but the networking and the algorithm process to process the data, you know. Other,
I'm glad you asked that question because I was wondering the same.
okay, did that answer it? Or did you need more answer, Paulette?
Yeah, that helped. Thank you.
Okay. I guess the other thing that I would say for the STIG that, I guess it's what I said in the video also, that bringing the people together from these different ideas, I don't know how many of you were at the current grantees meeting, but he was talking about bringing a teacher who teaches, or a student who's taking computer science and a student who's a pre-service teacher, and bringing them together to create a lesson. We were doing that on this larger scale of teachers, you know, who, you know, faculty from both of these areas and graduate students from both areas, and in-service teachers and pre-service teachers, basically trying to get input from all these different sides because it's such a fast moving and nebulous area that you really need to be coming at it from all these directions to truly understand it. So it's what I like to do, because my background is rather strange. I am faculty in the computer science department, but I also have a PhD in education. So I tend to branch that line better than some, but I love to see when we bring people from both sides together.
Well, this is good for me because I'm seeing it from a very different perspective for the first time. Because to me, I'm actually an engineer and taught mechanical engineering for almost 30 years, but I have used computer science and cybersecurity tools, a lot in that practice. To me, computational thinking was always really the approach of computer methods, how the data was collected, and not necessarily thinking about it as the network involved or the, kind of like that pre-process almost that has to happen. So I'm thinking more about the programming and the critical thinking skills and the logical sequences and the algorithms and those things more so than the things that you've introduced.
Yeah, we really want elementary teachers especially to see computational thinking as this broad coverage of all the topics that are needed to make people ready for computing. Because if we tie it too closely to programming and that aspect, there is a big problem, because programming is often seen as studying the computer for its own sake. And that tends to eliminate the populations that are currently underrepresented in computing. And so it's really important that we get that broader definition right from the start.
Can you elaborate on that point? You said that focusing on studying the computer for its sake, it eliminates populations. What do you mean by that?
The research shows that women and minorities are more interested in computers when you talk about how it is applied to real world problems. Where I'm a computer scientist from the late 70s, early 80s, so you get the reference. Then computing was taught more as what can the computer do? Not about what it can solve, but can we make this computer program faster? Can we, it was so much more about studying the computer for the sake of the computer, to understand the computer itself. So unlike biological science, which is studying biology to understand biological entities, computer science isn't studying the computer to understand the computing entity. It is to study what a computer can do for the world, because computer science has to be applied to something. Does that help?
Yes, it does. Thanks. That makes a lot of sense.
And in my work in diversity, that's something that has come up in the last 2 decades, that if we can get it to teach, and I think that was one of the main motivations for computer science principles, because computer science principles has the application of what computers are used for, where the computer science A is so unpopular with girls and minorities because it is studying programming for programming's sake. Any other topics you want to discuss?
Can I just ask a question about
Sure.
So usually computational thinking, when they define computational thinking, it's algorithms, patterns, abstraction, and decomposition. And sometimes a few other things are added in there. So I just want to get given what you said about expanding the definition, I want to get your kind of take on that and how to expand that.
Well, I do think all those parts are in there, but a lot of those actually fit into the programming portion. Like decomposition, we're talking about how to take a problem, break it down into pieces that the problem the program can do. Algorithms is part of programming. And so a lot of people tie computational thinking too close to programming. And actually, I want to put this in too. People tie programming too close to computer science. These are separate topics. And if you see computer science as part, or if you see programming as what computer science is, or programming is what computational thinking is, we're missing the boat. And now we had two people join us who are experts from our STIG-CT. The website I was showing you was created by Marika, who just joined us. And Kelly has written several of the papers about the I get those letters mixed up, CT, the larger project that the STIG was part of. So you guys can unmute and tell your point.
Hello, everyone. We just joined to see what you were saying, Jan. We're presenting in the next set of breakout rooms, so we just wanted to come in and say hi.
And they are both from the College of Education, but I've worked, with them a lot on these things because
So
we have to bring together the people.
I work with out of school programs as well. Is it okay to use some of these lesson plans that are available at that website? Is that okay?
Definitely, yeah.
Yeah, I mean, I use Scratch Junior, a lot of different programming a lot, but it's always nice to see somebody else's way, especially since you guys have done all the research on educational approaches. So that'd be great. I appreciate it. I'll definitely tell people where I got it.
The content was designed for teaching teachers.
Right, that's what I do actually.
Oh, great.
Yeah.
Okay. I'd like to talk to you more about that because that's what I do a lot too. So, I guess I thought we'd take a little more. I went fast through the other parts.
I have another question for you.
Yes.
So what are your thoughts on how to communicate that which you just discussed about computational thinking and programming, how to discuss that with early childhood educators like kindergarten, pre-kindergarten, first grade, and how those teachers would be able to communicate that understanding to a first grader, or is that not the goal?
No, that is the goal. But I think the way that I'm going to answer the second one first, and Kelly and Marika chime in if you disagree. But I think the way it gets from the teacher to the students has to be more in a subtle way, as in, here's something, you don't want to center it all around programming. So you want to talk about what the computer can do, and in a totally separate lesson, talk about how you'd make the computer do these different things, So it has to be sprinkled in a lot. For the pre-service teachers, when we're doing that, I think it has to be more overt, you have to be direct, because if you think about it, a lot of the people who go into elementary ed are because they don't necessarily like science and the STEM areas as much as the more social science type parts. And so you have to be more direct in saying, this isn't what you might have grown up believing it is, and so you have to unteach them, where I'm hoping if we can get the lessons correct for the elementary kids, we won't have to go through that unteaching part.
Thank you.
And I think the big thing is the constant, it's for the elementary students. It is the constant. It's like the earlier presentation of how to integrate it into math. We looked at how to integrate it into science. I did another project, which was NSA funded, of how to mix cybersecurity into language arts. If we can mix these things in all the way through, then we won't have as much problem with the diversity in computing, because everybody will see a way it fits into what they like best. So I think that's the most important thing we can teach to elementary pre-service teachers right now, and not to be scared of the computer in front of their students. I heard, too often people say, I don't understand this, we have to get somebody else to take care of it. We have to make things friendly enough that they're not ever saying that. Any other questions? Okay, so I had shared with you the overview. I think it's a good next step if everybody goes and looks at one of the vignettes. So everybody pick a random vignette. So I think this will make an interesting conversation point. Okay, so the
Are you
summary
sharing
is,
your screen so we can see?
no, I wasn't, because I wanted everybody to choose their own vignette.
And
I
I don't
can.
see those.
Okay, let me show you where I mean. Sorry, one quick thing. Okay, I'm going to share screen, and I'm going to share. I'm just going to share my screen, it'll be faster. Okay, so you see the, on the overview page, I'm going to back up one page. So the link took you here. If you go to the Stig Overview, each of these has a vignette. Then it opens in Word, so I'm not showing that, but. And so look at the vignettes. Oh, we have a vignette bundle, Marika. We could do that instead.
Yeah, I just dropped the link directly in chat to the Vignette Bundle because the page links directly to the instructions rather
Yes.
than to the things. And so the direct link to
Yeah,
that
to
is
get to
now in the chat for you all, so you don't have to try and trace through a couple documents.
Yes, she knows the structure much better than I do. Okay, so yes, go to the Vignette Bundle. And everybody pick a vignette. And once you read one, unmute yourself and tell us what you think about that as computational thinking. Okay. So I believe no, I'm not. Actually, I don't want to share while you're reading because then it takes over your screen.
So I looked at the one between precipitation and temperature, and the focus is more on the inferences from the data. So it reminds me of more of what we did when we were kids, because I think you come from the same generation as I do, where you were critical reasoning skills was something you were often evaluated on. So it's like critical reasoning, logical thinking, being able to make inferences, extrapolating data. So it was a very good exercise in terms of all of those skills.
Okay. Notice how a lot of times it overlaps into critical thinking and the mathematical reasoning and all those. I don't think it's important that we silo computational thinking off from these other things. It's just a set of skills, you know, we have to have some gray area, is what I'm saying. And that's okay. We have to be comfortable with that, because there's no way we can separate each type of reasoning kids need. But it's really important that students see this as a computational thinking skill. It was also really interesting you brought up generations, so I'm going to do that. When we did research on these vignettes, to see the different age groups saw as computational thinking. So the kids who were currently in college had a little different view on computational thinking and what it would be defined as compared to older folks. Somebody else have a vignette? We only have 1 minute left, so.
I read the pollination one.
Okay, and what did you think about it?
I'm not sure. I need to probably think about it a little more. I didn't necessarily see computation, but it's kind of like a simulation. So that would be where I would put it, but that's as far as I got.
I looked at number 1.
Okay.
I saw computational thinking in that the students were going outside, they were collecting data, whether a rock with moss on it was alive or not alive. And then when they went back into the classroom, they had to share an analysis of their thinking. And I would even say just the instructions themselves of go outside, number 1, observe plants and animals, such as squirrels and birds. Number 2, record your observations. I don't think we ever, and this is a very simplistic way of describing an algorithm, but I don't think that we ever narrow that down with our students and or our pre-service teachers.